In the last lecture, we had started looking at the path integral. In particular, we had seen that in order to calculate the propagator for a particle in one dimension to move from a configuration I, which is just my shorthand for xi and ti, position xi time ti, to a position xf tf, this propagator can be calculated using this formula. You integrate over all paths, and this curly d of x is a measure which essentially tells you that you are integrating over all possible paths that particle can take between ti to tf, and what you integrate is this quantity, a phase factor exponential I by h cross times the action, where s is the action calculated along the path taken. Well, this formula is going to be very useful for various manipulations and various indirect calculations that we are going to do in a while. But if you ever want to directly calculate the propagator using the path integral, you will have to fall back on the actual definition of this quantity, which is limit as n goes to infinity of this integral txj, I put the index in the wrong place, integral from j equals 1 to n, so there are n position integrals in all here. Then comes a factor h cross I epsilon to the power n plus 1 by 2, and then the actual integrand, which is, so this all of this was part of the measure here, the curly d of x, and then comes the actual integrand, which is the exponential of I by h cross times s, which when you discretize turns out to look like this, exponential I epsilon by h cross sum over j equals 0 to n. So just one reminder once again, there's one more term in the sum here, then there are integrals here. There are n plus 1 terms, 0 to n in this sum, and what you are integrating is m by 2 xj plus 1 minus xj by epsilon whole square, which remember is a discretized version of the kinetic energy, minus v at xj, the potential energy. So this is really the Lagrangian in that for that segment of the path, and you integrate all this, and then you end up with the result. So this is your formula for calculating the path integral. Of course, let me remind you that the epsilon here is a time interval for one slice, that you take the total time interval tf minus ti and you put n points in between the initial point and the final point. That makes n plus 2 points in all, which means n plus 1 interval. So this really is a connection between n and epsilon, and when you take the limit as n goes to infinity, of course epsilon goes to 0 in such a way that epsilon times n plus 1 stays tf minus ti. So this is the procedure under which you have to take the limit. Now a direct calculation of the limit can be done only for very few cases. So this explicit formula for calculating the path integral can give you an explicit result only very rarely. But in the cases where it can, it's sort of instructive to learn how to do this integral. One particular case where we can do this integral rather easily, well, easily is a relative word, but still more easily than for other problems, and one for which we have the advantage of already knowing the correct answer, is the free particle. As you may recall, we had already figured out the free particle propagator in the very first lecture by And we did that by using the momentum space expansion for the wave function. Now we are going to do this by using this formula directly. Okay, so let's see. Now, of course, for the free particle, this expression simplifies a bit. K from the initial state to the final state becomes limit as n goes to infinity. I'm just rewriting whatever we had over there. Product j equals 1 to n dxj. Now, let me just point out one thing. For the free particle, there is the potential. So you have m by 2 epsilon square inside the sum here, which can of course pull out of the sum. And if you do that, you are going to get Im by 2h cross epsilon, which of course is very similar to what you already have here. M by 2 pi h cross epsilon I epsilon. So there's an extra pi here. Other than that, it's essentially the same factor. So it makes sense to actually simplify our notation a bit by introducing this abbreviation. Let's call m by 2 h cross I epsilon alpha for the time being. That will simplify the notation a lot for us. So in particular, what that will do is this big factor, this m by 2 pi h cross I epsilon to the power n plus 1 by 2, this will simply become alpha by pi to the power n plus 1 by 2, and inside the exponential, what you will get is this sum will become minus alpha. Minus simply because here you have an I in the numerator, whereas our definition of alpha has I in the denominator. So that's minus alpha summed over j equals 0 to n xj plus 1 minus xj whole square. Things are complicated enough as it is, so we will take whatever small simplifications we get, including small simplification of just relabeling a few constants. Okay. So this, of course, is of the form limit as n goes to infinity of, let's call this Kn. So Kn is the nth approximation to the actual propagator, which is what you get when you do a finite number n of these integrals. So Kn, of course, is nothing but whatever you have here without the limit as n goes to infinity. What will make life a bit easier for us soon is that there is a nice way of writing Kn in an iterative fashion, which means that if you know Kn minus 1, you can carry out only one integral and get to Kn. After all, this is a multiple integral, and multiple integrals are done iteratively. So you can easily see that this formula that we have written down can simply be written by separating out the integration over the nth variable. You of course still have integration over the other n minus 1 variables to be done. J equals 1 to n minus 1 now. Let me just make some space here. I put the integral sign too close. Okay, so this is the n minus 1 integrals. Of course, if you are doing this n minus 1 times, then I would expect n minus 1 to sit everywhere where n is sitting now. So instead of n plus 1 by half, I would want this to be n by half. Of course, that can happen only at the expense of an extra root over alpha by pi. And what about this exponent? Well, being an exponent is easy. Remember, in a path integral, everything is classical. There are no operators left. So all you can do is write the nth term separately, xn plus 1 minus xn whole square, and then write the rest j equals 0 to n minus 1 xj plus 1 minus xj whole square. So all we have done is we have separated out all the terms which involve n's explicitly, and this will simply lead to this simple result which we are going to exploit. dxn root over alpha by pi to the minus alpha xn plus 1 minus xn whole square. Notice that as far as the other inner integrals are concerned, the integration variables are x1, x2, x3 up to xn minus 1, which means this xn here is a constant as far as the inner integrals are concerned and can be pulled out. And once you do that, it's easy to see that the nth approximation to the propagator can be found out from the n minus 1th approximation just by doing one more integral, and the integral is just this. The question is, can we do this integral at all? Or can we do it explicitly? The answer is, at least for this simple case, we can, but it's better that we start slow. And what I'm going to do is I'm going to remind you first of the basic formula that we will need throughout. We actually have met it quite often. In fact, we made it in the very first lecture when we did an explicit calculation of the propagator for the free particle. This integral, the standard Gaussian integral, just to remind you, this works out to root over pi by a e to the power b square by 4a plus c. There is one condition that has to be followed. Real part of a has to be positive for this integral to converge. And just as we have done several times already, you will realize that the integral that we have to do in this case also suffers from the problem that we have a purely imaginary a in our cases. So in order to make sense of the integral, what we have to do is add a small positive real part to this a, do the integral, and then take the additional piece away by taking the limit as this goes to 0 from the positive side. Now I'm not going to do this explicitly. I'm just going to assume that you understand that this is the procedure that we use to make this integral converge. Now, getting back to the actual calculation, this was the formula that we have to work with. Root over alpha by pi, integral over all space over the nth variable is a minus alpha xn plus 1 minus xn whole square an minus 1. Now, let's start small. Let's start with just one integral to be done, k1. Now, of course, k1 cannot be written in terms of k0, or actually it can. But then I have to adopt the convention as to what exactly k0 is. But let's not get into that. Let's calculate k1 directly from the original formula, which is only one integral, j equals 1 to 1. Then you have an alpha by pi to the power n plus 1 by 2. That's one factor of alpha by pi. Then you have this exponential, which is the sum over two terms. J equals 0, j equals 1. So minus alpha x2 minus x1 whole square minus alpha x1 minus x0 whole square. And the integration, of course, is only over x1. x2 and x0 are constants as far as this calculation is concerned. So let's take all the constants that we can find, and multiplicative constants can of course be pulled out of the integral. One such factor of course is alpha by pi, and in the exponent itself, if we expand it out using our old favorite formula, a plus b whole square or a minus b whole square, we get this result. x2 square plus x0 square can be pulled out from the inside the exponential, and then you are left with minus infinity to plus infinity dx1 exponential minus alpha. Now let's gather all the terms together. You get 1x1 square from here, another from here. So 2x1 square. You also get minus twice x2 x1 from here, minus twice x0 x1 from here. So minus twice x2 plus x0 times x1 from here. Or the integral that we have to do is of the form e to the minus ax square plus bx plus c, but with small a equals minus 2 alpha, right? Minus alpha into this 2, and small b equals 2 alpha x2 plus x0. So this is a standard Gaussian integral, can be evaluated directly from the formula above. Let me remind you once again, our alpha really is purely imaginary. If you have forgotten, our alpha is m by 2 pi h cross I epsilon. So it's purely imaginary because of this I sitting here in the denominator. So strictly speaking, this integral does not converge and we have to make it converge, but we already know how to do that. So let's move on and calculate this result. You get alpha by pi is the minus alpha x2 square plus x0 square sitting outside, and then we write down the result for the Gaussian integral, which is root over pi by 2 alpha. Okay, and then you have e to the power plus b square by 4a. There is no c here, c is 0. So b square is 4 alpha square x2 plus x0 whole square, and then you divide it by 4 times a, that's 2 alpha. So the 4's of course cancel each other out, the alpha cancels one factor here, and now you have this final result. This alpha by pi and root over pi by 2 alpha of course cancels a bit, you get root over alpha by 2 pi. Then inside the exponent, let's collect everything together, minus alpha. In fact, it will be easier if I took there's a by 2 in this factor, so I take the by 2 out, and I get twice x2 square plus 2 x0 square minus x2 plus x0 whole square. And now it's a matter of simple high school algebra to simplify this a bit and end up with root over alpha by 2 pi exponent minus alpha by 2, and okay, it takes no great genius to work this out. This simply is x2 minus x0 whole square. So K1, one integral is sort of easy to do. You just do a simple Gaussian integral and you are done. You have got this result. Of course, we have n of these to do. So let's now look at K2. So how much is K2? Well, I don't have to do two integrals now because I have this iteration formula for us. I just take in a root over alpha by pi and this exponential factor and kn minus 1, which in this case is K1, and integrate. So I get root over alpha by pi dx2, and then stick in the factor exponential minus alpha x3 minus x2 whole square and k1, which of course is root over alpha by 2 pi. It is a minus alpha by 2 x2 minus x0 whole square. So let me remind you once again that for this integral, x3 and x0 are constants, only x2 has to be really integrated over. So let us now simplify by gathering all the constants together outside. So what you get is root over alpha by pi, which was already outside. Then you are pulling out an extra root over alpha by 2 pi. Before we start writing the integral, there's one more term that we can pull out. That's e to the power minus alpha. Now we have to be careful. You get x3 square from here, and we get x0 square by 2 from inside this factor. all the other terms have x2 in them, so they can't be pulled out of the integral. They have to be part of the integral evaluation. So now you have the integral over x2 of this exponential. We have to be careful in gathering the terms together. You get minus alpha, which is common to all terms. Then you have an x2 square from here and an x2 square by 2 from here. So you get 3 by 2 x2 square. Now you get twice x3 x2 with a minus sign from here and twice x2 x0 from here. But there's a by 2 in the second term. So it's twice x3 plus x0 by 2 into x2. And this is the integrand that we have. Just to point out, we once again have the standard Gaussian form. A now being given by 3 by 2 alpha and B being given by twice x3 plus x0 by 2 alpha. So it's pretty straightforward to calculate the integral now. First, the constants that were outside. Now you have to multiply that by the result of the Gaussian integral, which is root over pi by 3 by 2 alpha, so 3 alpha into a 2. And notice that there is a huge amount of cancellation that you can do right here, because this 2, this pi, this alpha, all of them cancel out this whole factor. But we are yet to write down the most important term in the calculation, which is the exponential, which you get by calculating b square by 4a. So b square is 4 times x3 plus x0 by 2 whole square, alpha square of course, divided by 4a, that's 4 times 3 by 2 alpha. So this 4 and this 4 of course cancel out, this alpha takes away one of these alphas, and you are left with some terms which you have to now gather together. So root over alpha by 3 pi, exponential. Now let's do the gathering carefully. Since there is going to be a 3 down here, this 3 by 2 is of course going to end up being a 2 by 3. Let's take minus alpha by 3 common out. That gives you 3x3 square here plus 3 by 2 x0 square for the terms that were already outside. Now you have a minus twice x3 plus x0 by 2 whole square, which you have to deal with. But as you will soon find, this simplifies drastically. Over alpha by 3 pi, exponential, so this remember is k2, and this works out to minus alpha by 3, and you can easily see that if you square this out using our favorite a plus b whole square formula, I get 3x3 square minus 2x3 square here, that's simply an x3 square, the 3 by 2 x0 square minus 2 by 4 x0 square, simply gives you a single x0 square, and then you have a minus twice x3 x0 from here, so this is simply x3 minus x0 whole square. Just to contrast, let's put down k1 right next to it. K1 worked out to be root over alpha by 2 pi, exponential minus alpha by 2, x2 minus x0 whole square. Now I know that it's dangerous to extrapolate from just two examples, but if you have two terms, k1 and k2 written down like this, I'm pretty sure most of you would definitely love to guess that kn, or let's write down kn minus 1 for the time being, kn minus 1 will be root over alpha by n pi. Notice that this is one more than whatever index you have here, minus alpha by n, xn minus x0 whole square. At least this is what you would love to guess. Guesswork of course will not really get us anywhere unless we can back it up, and as you all know, in situations like this, you can easily back this up by using what is called the principle of mathematical induction, which is I need to show that if this formula is true for some n, is true for the next one. So Kn, if you calculate that, will also have to fit the same pattern. Of course, that's not enough. You also have to show that this equation is true for some n at all, but we already have done that, right? We have actually guessed this Kn minus 1 form using the examples that we have already calculated for K1 and K2. So at least we know that this is valid for some n. But how do we prove that this is going to work for the next n? So Kn is equal to this result that we already know. Kn is minus infinity to plus infinity dxn, the minus alpha xn plus 1 minus xn whole square times Kn minus 1. So let's see whether we can use this to find out whether the result that we had surmised actually holds up. Xn plus 1 minus xn whole square. Let's put in our presumed formula, root over alpha by n pi inside, and now let's check whether we can massage this into the same form as Kn minus 1 had, with only n substituting n minus 1. So once again we follow the same pattern. It's essentially the same calculation done over and over again. The only reason why I'm showing you this over and over again is that it's pretty useful to get some practice in doing this kind of calculation. So then we pull out the constants once again, xn plus 1 whole square from this factor and x0 square pi n from the factor inside, and we are left with a Gaussian integral to do. dxn now once again rather carefully, let's collect all the terms together. You get an xn square from here and an xn square by n from here. So it's n plus 1 by n, 1 plus 1 by n, which is the same as n plus 1 whole divided by n, xn square, minus twice xn plus 1 times xn and x0 times xn. So xn plus 1, but the x0 of course comes with a 1 by n outside. So that's it. That is the integral that you have to do. So once again, let me identify the a and b for you. A is simply n plus 1 by n into alpha, and b is twice xn plus 1 plus x0 by n into alpha. Okay, and this finally gives you the result. If you collect all the terms together, get root over alpha by pi, root over alpha by n pi, alpha xn plus 1 whole square plus x0 square by n. Now comes the result of the Gaussian integration. Root over pi by alpha, n plus 1 by n, so the n goes up there. And we are already seeing glimmers of hope, because what we can see is this alpha n pi cancels out, and you are left with root over alpha by pi n plus 1, which of course is great, because that's exactly what you would expect in the next step of the formula. And the Gaussian integral itself, b square by 4a, works out to be xn plus 1 plus x0 by n whole square. That's the b square. Of course, there's a 4 alpha square which you get also, but the 4 will cancel. You will be left with 1 alpha, but you will also have n by n plus 1. So all that remains is now to gather all the terms together and try to see whether we can put this kn expression in the form of kn minus 1 with only n substituted for n minus 1. So now let's open one more page and go on from here. So gathering all the terms together, what we get is root over alpha by n plus 1 pi, which, as I said, is a big, hint that we are on the right track. And what about the exponential terms? Now, once again, I will take the n plus 1 common out along with alpha. Now, inside what we have is n plus 1 times xn plus 1 whole square plus x0 square by n. These are the constants that were already there before the Gaussian integration. And then you have minus n xn plus 1 plus x0 by n whole square. And now the simplification is sort of straightforward. Root over alpha by n pi exponential minus alpha by n plus 1. If you gather everything together inside, here you have n plus 1 x plus n plus 1 whole square. You have n xn plus 1 whole square from here. So you just get 1 xn plus 1 whole square. Here you have n plus 1 by n. That is 1 plus 1 by n x0 square. And you have an 1 by n x0 square from here. N times x0 square by n square. So again, everything neatly cancels and you end up with this. And when you take the twice ab term from here, you simply get twice xn plus 1 x0. Of course, this is exactly what you saw in the previous two cases. This same simplification occurs. And sorry, I made a mistake here, of course. This factor here is root over n plus 1 pi. So finally, we end up with this result that kn is root over alpha by n plus 1 pi e to the power minus alpha by n plus 1 xn plus 1 minus x0 whole square. So what we have managed to do is we have managed to prove that the induction hypothesis works here. The form for kn minus 1 is repeated here for kn only with n substituting for n minus 1. We already know that k1 is correct. So is k2. That is, k1 and k2 have this form. And so all kns have the form by the principle of mathematical induction. So we have explicitly worked out the form for kn. All that remains to find our propagator k I to f is to actually take the limit as n goes to infinity of this expression. And let me just, in the interest of taking the limit, let me put back for alpha the factor that this really stands for, n plus 1 epsilon pi twice h cross I. So that's what substituting the alpha back gives here, an exponential minus the same factor except for the pi, n plus 1 epsilon times twice h cross I. Now xn plus 1 is nothing but the final x, xf, and x0 is nothing but the initial x, so xi whole square. Now the limit essentially becomes very trivial, because the only thing which depends on n are here n plus 1 and epsilon, and here. And we know that n plus 1 times epsilon is tf minus ti. So the limit simply works out to be m by 2 pi h cross I times tf minus ti, and in the exponent itself what we have is exponent of minus m by twice h cross I tf minus ti xf minus xi whole square, which, if I may remind you, is exactly what we figured out using the momentum space expansion in the very first video. And just to remind you once again, this m into xf minus xi by 2 tf minus ti is nothing but the action for the classical path. So in this particular case, at least, what we get is the action, although it's really a sum of phase terms from each and every path. For the free particle, it works out that ultimately the propagator is proportional to the contribution which comes from the classical path only. Now this is a simplification which occurs only for the free particle, as I have emphasized before. So please don't expect this to recur everywhere, or not only for the free particle, but for a few other systems besides, and we are going to meet them soon. So this is one approach towards calculating the path integral. Now we will talk about at least a couple more methods for calculating the path integral directly. The next method we are going to talk about generalizes the Gaussian integral. This, of course, is the Gaussian integral which we have been using so far. And although it's really not necessary to tell you all this, but let me just quickly remind you that the way in which you derive this essentially uses high school algebra, in the sense that what it does is it completes the square. So it writes this as x square minus b by ax, but you need a 2 here to make a perfect square, and you put in a by 2 there, plus a c, and then you complete the square by supplying the b square by 4a square along with it. So minus b by twice a whole square. And of course, if you are subtracting the b square by 4a square from here, you have to add it back, and since there's an extra a outside, you end up with b square by 4a plus a c. And so the integral that you are doing ends up being e to the minus a x minus b by twice a whole square plus b square by 4a plus c, this whole exponential integrated from minus infinity to plus infinity. And the next step that we use is just say that if you shift the variable from x to x minus b by 2a, so you change your variable from x minus x to x minus b by 2 I say, which we can call, say, y, and this of course causes no change in the measure, dx is the same as dy, and you end up with the integral e to the minus a y square dy, apart from the e to the b square by 4a plus c, which is a constant which you can take outside. And the critical step here is to realize that this shift does not change the limits. Now, there's a bit of a tricky issue here. You might say that taking away a constant amount from both the upper and lower limits of an integral, where the limits are both infinite, should not make a difference. And this argument would be almost perfect if what you are taking away were real. But in general, b by twice a could also be complex or purely imaginary. What that means is that instead of doing the integral over the real line, for which we know the answer, we actually end up doing the integral over a line which is actually not along the real line from minus infinity to plus infinity, but actually somewhere, say, above or below a line like this. Now, the claim that I'm going to make is the integral along this shifted line is the same as the integral along this line, and this is the result which follows from elementary complex analysis. So I will urge you to worry about why this should be the case. Just think of where the singularities of the function to the minus ay square are and so on. But anyway, this rather trivially gives you the same result as doing the integral over the real line, and that of course is root over pi by a to the minus is the b square by 4a plus c. Anyway, this is a result which we have been using all along. And frankly, I don't think any of you needed a proof of this result. If you are studying path integrals, you definitely have studied things as simple as the Gaussian integral before that. But what I'm going to do now is a generalization of the Gaussian integral to multiple dimensions. So just like you had a Gaussian integral where the exponent was a quadratic, but in one variable, let's go over to a situation where the exponent again is a quadratic, but of multiple variables, let's say x1 to xn. So what you have in the bracket up there could be something like a11 x1 square plus a22 x2 square plus a33 x3 square and so on. And of course, you don't really necessarily have to add in there. You could also have cross terms like x1, x2, x2, x1 and so on. Plus twice a1, say 1n x1 xn, all the way down to twice an minus 1 n xn minus 1 xn. I'm pretty sure most of you realize that I could have written a1 to x1 x2 plus a21 x2 x1 here. The reason why I did not bother to do that is that since x1 x3 is always the same as x2 x1, remember that's true only because the variables that we are using here are ordinary real numbers, they commute. So a12 x1 x2 plus a21 x2 x1 can always be combined together, and it always comes out as a12 plus a21 x1 x2. And even if your original a's were defined in such a way that a12 was not equal to a21, I could always take the average and call that the new a12 and get the same sum. So what I'm going to essentially say is that a12 will always be taken to be equal to a21, and in general aij will be taken to be equal to AGI. This is not the only possible term, right? These are the quadratic terms. You could also have, in addition, terms like b1 x1 plus b2 x2 plus bn xn, and then of course a term which is independent of the x's, which is c. Now there's a compact way of writing all this. Well, c of course is simple enough, you can't really make it any more compact, but b1 x1 plus b2 x2 plus bn xn looks very much like the dot product of two vectors. Or if you use a standard column vector notation, column vector row vector notation, that is, if you were to define a column vector like this, let's call this x with a tilde below, just to denote that this is not a single x, it's really x1, x2 all the way down to xn, a column vector. And similarly, if I define b with a tilde below again as a column vector with b1, b2, bn as its elements, it's easy to see that this term can be written down as b tilde t x tilde. What about this whole complicated term involving the quadratics? That's also really rather simple, and I'm pretty sure most of you have seen this before. You can always write this in what is called a quadratic form, x tilde a, and while you're putting tildes everywhere, why not put a tilde under a as well? X tilde transpose, where a tilde is this matrix, n by n matrix with elements a11, a12, a1n, a21, a22, a2n. We are assuming that this matrix is symmetric, that is, all the aij's are equal to ajis, and then finally all the way down to ann. So if you assume that, our Gaussian integral that we are going to do can be written in this form. Now I realize I forgot to tell you one thing. I did say that we are going to increase the number of variables. I did not mention, although it should have been sort of obvious, that we are going to integrate over each and every one of these variables from minus infinity to plus infinity. So the Gaussian integral now is not over one variable x1 or x, it's over x1 to xn. So the integral that we are trying to do is this: dx1, dx2, dxn. All these integrals will be from minus infinity to plus infinity. And you will have an exponent which we are writing in short, and I'm going to drop the tildes below now because I assume that you should be able to understand perfectly well whether we are talking about a single variable or a column vector just from the context. So xtax plus btx plus c. This is our final form. Just to sort of contrast this with our original integral, that was minus infinity to plus infinity dx, it is a minus ax square plus bx plus c. Now, of course, you should be able to understand exactly why we are talking of an integral like this. The integral that we had to do over n variables to find out kn, the propagator's nth approximant, is exactly an integral of this form for a specific choice of the matrices A, B and C. So we are right now trying to work out the Gaussian integral in multiple dimensions in general, a result that will be quite useful in many applications. So let's look at the exponent that we have. We have minus xtax, which is a purely homogeneous quadratic part, plus btx, which is a linear part, plus a constant. Now, our aim would be, just as we did here, to get rid of the linear part. Here also, remember, completing the square was essentially done to get rid of the bx term. So here, let me assume that we are going to write x as y plus some column vector. So x is a column vector with n variables, so is y, but you add some constant vector to this. Let's call that constant vector, for want of a better name, let's call it t. So if I substitute here, I get y plus t transpose a y plus t plus b transpose y plus t plus c. That's what our exponent is. And now we can expand this out. You get 4 terms from the first piece, y transpose ay, a homogeneous quadratic in the new variables y1, y2, yn, plus 2 terms which are linear in y, t transpose ay, plus y transpose, okay, these are all minuses because of the overall minus sign outside. So minus t transpose ay minus y transpose at minus t transpose at. These are the 4 terms which comes from the first term here. From the next term, what we get is 2 terms, one of which is linear, another which is just a constant, independent of y completely, and finally the term c as it stands. Now our aim would be to get rid of the linear terms in y. So what we want to do is get rid of this term, this and this. And what makes it a bit easier for us is the realization that these 2 terms are actually equal to each other. The way you prove that is the following. First of all, you realize that since A is an n by n matrix and T is a n by 1 column vector and y transpose is a 1 by n vector, a row vector, the overall product here is just a 1 by 1 matrix, or really just a number, which means it has to be equal to its transpose. If you take the transpose of yt at, which is the same as itself, of course you end up with t transpose a transpose y, but since A by our choice has been made symmetric, we get t transpose ay, which is the same as this term. So the 2 linear terms here combine to give you twice t transpose ay with a minus sign, and you have plus b transpose y here. So the condition that we want to impose on our t is simply this. Twice p transpose ay must be equal to b transpose y so that the linear term goes away. That's our aim. So how do you achieve that? Straightforward. You achieve that by demanding that twice t transpose A is equal to B transpose. That's how you choose your T transpose or T, and that means of course twice A T by taking the transpose is simply B, which implies T is half A inverse, and for the time being we're assuming that A inverse exists. A inverse times B. So once we have made this choice, what happens? What happens is our quadratic simplifies considerably. All these terms go away. And what is left is a purely homogeneous quadratic piece here and these terms which are just constants. And the constants can also be simplified considerably. So now this is actually the same now as minus y transpose ay, which is the pure quadratic piece. Now notice that minus t transpose at, since t transpose A is half of B transpose, is simply nothing but half of B transpose T. So this overall thing is plus half. This is really minus half of B transpose T, this term, and you have a B transpose T here. So you get half of B transpose T, and by using the value of T, I get 1/4 B transpose A inverse B plus a C. By the way, when we did this with one variable, what we ended up with is B square by 4A plus C here. You can see that B transpose A inverse B by 4 is a direct generalization to multiple dimensions of the term B square by 4A, which we had for one variable. So this is the integral that you finally want to do. Of course, you have to change your integration variable from x to y, but since the difference between x and y is just a constant, the change of variables is rather trivial. All dx1 is the same as dy1 and so on. You end up with e to the minus y transpose ay, the pure homogeneous part. So this is our integral that we wanted to do. And then comes this piece, which is just a constant, P transpose A inverse B plus C. We are still not done, but we are quite a long way to our goal, and this is the only integral that we do. This, of course, is a constant. It can be taken outside the integral. Now, how do you do this integration? This is where a very important result comes in handy, which is that a symmetric matrix is always diagonalizable. And not only is it always diagonalizable, it's always orthogonally diagonalizable. Which means you can diagonalize it by an orthogonal transformation. Now, why is that a great thing? Just think about it this way. Suppose I change y to a new column vector by saying that y is, say, some matrix, square matrix S acting on Z. Not just any square matrix, some orthogonal matrix. Then yt, of course, will be zt st, and so the exponent here will be e to the minus zt st as z. So that's what this e to the minus yt ay will become. And what will happen here is, of course, what you need is the measure will, of course, have to change to dz1, dz2, dzn. And this then has to be multiplied by the Jacobian of this transformation from y to z. But if you think about it a bit, the Jacobian for a linear transformation is nothing but the determinant of the matrix which does the transforming, in this case determinant of S. And since we have chosen S to be orthogonal, this determinant can be easily taken to be 1. In fact, you can always choose it to be orthogonal with determinant plus 1. I hope all of you remember that an orthogonal matrix can have only two values for its determinant, either plus 1 or minus 1. And we can always choose by rearranging the columns to get a determinant plus 1 matrix. So, this transformation, changing y1, y2, yn to z1, z2, zn, does not introduce any change in the measure. But what it does do is it changes the matrix here to a similar matrix. Remember, S is the orthogonal, so S transpose AS really is the same as S inverse AS. And what we can achieve here is by choosing the matrix appropriately, we can do a similarity transformation such that A becomes diagonal. So this is what is important. You can always orthogonally diagonalize the matrix. Of course, the diagonalization process requires you to calculate all the eigenvalues and eigenvectors and so on. But you don't really have to carry out the whole calculation to understand this result. All you need for the formula that we are going to derive is the knowledge that you can diagonalize it. So once it's diagonalized, then of course this integral simply becomes dz1 to dzn, and this zt dz, where d is just diagonal, simply becomes minus lambda 1 z1 square plus lambda 2 z2 square plus lambda n zn square. All the off-diagonal terms are the ones which were giving rise to the cross terms before. They have all gone away. Now this is very simple, because all you are doing now is you are going to do the integral, this integral, in this fashion. You are going to just do dz1 e to the minus lambda 1 z1 square, dz2, all these integrals decouple, and you are left with n one-dimensional integrals to do, each of which are things whose results you know perfectly. This one is root over pi by lambda 1, this one is root over pi by lambda 2, and so on, and this is root over pi by lambda n. Of course, what is critically important here is that we are assuming that all the eigenvalues are non-zero. In fact, we are actually assuming that all of them are positive. But once you make that assumption, you get pi to the n by 2 in the numerator. In the denominator, you get square root of the product of all the eigenvalues, which of course is nothing but the determinant of the matrix S. So, the final result does not require you to actually know all the individual eigenvalues and eigenvectors. All you really need is the determinant. So, finally, our formula for multiple Gaussian integral dx1, dx2, dxn is the minus xtax plus btx plus c becomes pi to the n by 2 by root over determinant of, sorry, this is not determinant of S, this is the determinant of the original matrix A. Then it's the same as the determinant of the matrix D. The determinant of the matrix D is of course the same as the determinant of the matrix A. E to the power 1/4 B transpose A inverse B plus C. So the calculation of the Gaussian integral requires you to only know the determinant of the matrix A and the inverse of the matrix A. And that's it. So we are going to use this now to calculate our path integral for the free particle. Armed with this result about the multiple Gaussian integral, let us now try to write down an expression for Kn using this. Just to remind you, Kn, the nth iterate to the path integral formulation for calculating the propagator, was simply this: dxj alpha by pi to the power n plus 1 by 2 times this exponential minus alpha sum over j equals 0 to n xj plus 1 minus xj whole squared. Now what we need to do is we need to separate out the constant terms and the terms to be integrated over in this expression. Realize that we are only integrating over x1, x2 to xn, and apart from these x's, there are two more x's in this expression. They are xn plus 1, the final x, and x0, the initial x. So those two variables, x0 and xn plus 1, are not being integrated out. So we have to keep track of them separately. So let me just try to write this with all the constants taken outside. Alpha by pi to the power n plus 1 by 2. Then constants, by that I mean terms which are independent of the integration variables, are here: minus alpha xn plus 1 whole square plus x0 square. These are the two terms which are not being integrated over at all. Then we have the integration measure, j equals 1 to n dxj, which is just a shorthand way of writing dx1, dx2 up to dxn. And then we have to note that we have terms which are linear in integration variables. Which terms are those? These are these terms, twice alpha x1 times x0. Notice that although x0 is here, it's not an integration variable. So there's only one power of an integration variable here, namely x1. And there's one such other term coming from the extreme bracket on the other side, which is xn plus 1. So these terms are the linear terms. This is our btx, these terms together. In addition, we have homogeneous quadratic pieces, and if we take all of them together, notice, for example, x1 actually occurs twice, right? Once in x1 minus x0 whole square, again in x2 minus x1 whole square. Taking that into account, I will get twice x1 square. Similarly, I'm going to get twice x2 square, and all the way up to twice xn square. All of these x's appeared in two different squares. Then we will have minus 2x1 x2, minus 2x2 x3, all the way up to minus twice xn minus 1 xn. So that's just what we had. We have just written this out in full. As you can see, the integrand here is exactly of the form e to the minus xtax plus btx. There also was a e to the c, but that has been pulled out here, where b, x of course is our column vector with x1, x2 all the way down to xn. B is rather easy to figure out because there are only two terms in the linear piece here, so there will be only two non-zero things. Okay, I had made a mistake. This is a plus 2 alpha, right? Because it was minus twice alpha x1, x0 inside the bracket, but there's a minus sign outside. So this is plus 2 alpha. So there will be only two non-zero terms in this B, x1, 0, 0, all the way down to xn plus 1. And finally, A is the square matrix alpha times 2, minus 1, minus 1, 2, minus 1, minus 1, because the minus 2 x1, x2 is being split into minus x1, x2, minus x2, x1 symmetrically. 0, 0, 0. So on down the line, this is basically going to be a what is called a tri-diagonal matrix. Going down all the way down to 2, minus 1, 2, minus 1, minus 1 here with zeros all the way. So this is an n by n tri-diagonal matrix with 2's down the diagonal and minus 1's on the semi-major or semi-major and semi-minor diagonal. The one just above the diagonal or the one just below the diagonal. So we have set up our form perfectly. So what we need now to calculate Kn is basically we need to be able to calculate the determinant for this matrix A. So what we really need here is to be able to figure out the determinant of this matrix A, and not only that, we need its inverse. Although frankly we don't need all the terms in the inverse, we just need A inverse 1, 1, A inverse 1n, A inverse n1 and A inverse nn. Simply because we are going to use A inverse in the quadratic form B transpose A inverse B, and B has almost all its terms equal to 0. So the only non-zero contributions will come from these 4 terms in the inverse. So it's really not the whole m square elements of the inverse that I have to calculate. It's a lot smaller task than that. For the time being, let's also point out one thing. Let's forget about the alpha for the time being. Let's put alpha equal to 1 at this stage, or just ignore the alpha. We can always put in the alpha in the final answer, right? Because if we can figure out the determinant of this matrix, then determinant of A is simply alpha to the n times that. And if you find the inverse elements of this matrix here, the one without the alpha, then the elements of A inverse will simply have an extra 1 by alpha in front of that. So putting back the alpha is really rather simple. So with that in mind, let's call the determinant of this matrix here without the alpha dn, because it of course depends on the size of the matrix. So what we will do is we will try to find out a formula for dn. Now, in order to find a formula for dn, what we will do is we will simply go by elementary matrix theory. If you look at the top row here, there are only 2 non-zero elements, 2 and minus 1. So you can expand this out by writing equals 2 times the cofactor of this plus minus 1 times the cofactor of minus 1. This minus 1 here. So let's see. If you want to find the cofactor of 2, you drop the row and the column containing 2. And if you do that, you immediately see that what you are left with is again a matrix of exactly the same kind. So its determinant will also be of exactly the same kind, with only one difference. It will have n 1 smaller. That is, this is 2d n minus 1. What about the minus 1? Well, with minus 1, when you're looking at minus 1, there are 2 things you have to worry about. Firstly, you will already put in a factor of minus 1 to the power 1 plus 2 here. That's plus minus. The second term comes with a minus sign in the determinant expansion. And then once I drop this row and this column, and now end up with a n minus 1 by n minus 1 matrix, which is not exactly the same as the one which I was working at before. Actually, though, it's not very difficult to handle because it has one column which has only a single minus 1. So the next step would be minus 1 times the cofactor for this. And once you do that, you will see that all you are left with is this n minus 2. By the way, this minus 1 was already part of the deleted elements here. So let's hope you did not get confused by this shoddy way in which I wrote this, but this minus 1 has already been taken care of when you drop this column. So you are now left with this n minus 2 by n minus 2 matrix, which is of exactly the same form, and you need to put down its determinant, which is dn minus 2. So dn, as we can easily see, obeys this recursion relation. dn is 2dn minus 1 minus dn minus 2. And we already know some values of dn. For example, with n equals 1, there's only one term, that's the 2 in the diagonal. So d1 is of course 2. d2 can be easily calculated. d2 would be the determinant of this matrix, and that would definitely be simply 2 into 2 minus 1 into minus 1 into minus 1, that's 3. Now, I'm not saying that from these two terms alone you can figure out what the answer is, but it should not come as a surprise that the solution to this recursion relation consistent with these values work out to be something very, very simple. I will let you figure it out yourself. dn just turns out to be equal to n plus 1 for this simple problem. So if you don't know how to solve recursion relations like this, I'm pretty sure you can find out on your own. And anyway, this is such a simple case that you can actually guess the answer and then establish the result by mathematical induction if you want to. Okay, so that much is done. You have the determinant for the n by n matrix. Now let us try to figure out the inverses or 4 elements of the inverse. A inverse 1, 1, for example. To find A inverse 1, 1, what I need to do, of course, is find out the cofactor of the 1, 1th element and divide by the determinant of the full matrix. So, to find the cofactor, get rid of this, and then you're done, because the cofactor now is simply obviously dn minus 1. So you can write down the A inverse 1, 1 rather trivially as dn minus 1 divided by dn, or actually, since we are talking about the original matrix A with the alpha, there will be an extra 1 by alpha from the alpha outside. So you get 1 by alpha n by n plus 1. That's A inverse 1, 1. You can easily check that that is the same as A inverse nn. So we only have this thing to calculate now, 1 comma n, which has to be the same as A inverse n comma 1, because A, remember, is a symmetric matrix, and it's a standard result in matrix theory that the inverse of a symmetric matrix is also symmetric. So let's go back and try to find out what A inverse n1 is going to be. So let's take a look at the 1n element. This is the one whose cofactor you want to find out. Well, for that you need to get rid of this row and this column. And now, first of all, what you will get, apart from the 1 by alpha, which is there outside anyway, is this. Below you will get the dn. In the numerator, you will have to put down the cofactor. The first thing in the cofactor that you already know is that there is a sign term, which is minus 1 to the power row plus column. In this case, 1 plus n. Times the minor, which is the determinant of this matrix. This n minus 1 by n minus 1 block here. Now this is actually absolutely trivial to work out, because this is a triangular matrix now. Notice that every element below the diagonal for this matrix is 0, and every element on the diagonal is simply minus 1. So the determinant for this is trivial to calculate. It's just minus 1 times minus 1 times minus 1, as many minus 1s as you have, which is n minus 1 minus 1s. And it's easy to see when you multiply these two things together, you get 1. So you get 1 over alpha n plus 1. So all the ingredients that you need to calculate the Kn is in your hands now. So what you do now is simply write Kn down. Kn is, okay, let me just remind, okay, you can, I think you should be able to remember the formula. Alpha by pi to the power n plus 1 by 2 e to the power minus alpha xn plus 1 whole square plus x0 square. These were the constant terms that you had pulled out. Then you will have simply pi to the power n by 2 by determinant of a. And what is the determinant of a? I found out dn to be n plus 1. From there I need to find determinant of a, but that has to be simply alpha to the n times n plus 1, right? So here you get alpha to the n by 2 over n plus 1. So that's the pi to the n by 2 by square root of determinant a done. And then you have it, the 1/4 B transpose A inverse B. But B transpose, remember, has only these terms. B is almost entirely 0, but you have twice alpha x1 and twice alpha xn plus 1. From the two alphas you get 4 alpha square. From the A inverse you get 1 by alpha. So putting them together you get the 4 alpha square, 1 by alpha, and the 4, they cancel out and give you alpha times. Now this is where the terms that I have calculated comes into being. X1 square, sorry, x1, the 1th position is occupied in B is occupied by x0, so x0 square is multiplied by n by n plus 1. There was a 1 by alpha which I had already taken into account outside, plus xn plus 1 square into n by n plus 1. So these are the two terms which come from A inverse 1 1 and A inverse 1n, A inverse nn. And from the A inverse 1n and A inverse n1, what you are going to get is plus twice x0 xn plus 1 by n plus 1. The 2 simply comes in because you get one term from A inverse 1n and another from A inverse n1. Now if you put them all together, you notice that a lot of stuff will cancel. Pi to the n by 2 will cancel with this, alpha to the n by 2 will cancel also. So you are left with alpha by pi root over n plus 1. And it's pretty straightforward to show by simply joining the exponents together that this is xn plus 1 minus xn whole square. So this is again, of course, not a surprise. We have already worked out Kn, and that Kn will come out to be this. Was a given because we already know the answer here. However, it's gratifying that by applying the method of n-dimensional Gaussian integrals, we can also figure out the propagator for the free particle. Of course, this is not the propagator. You need to take the limit as n goes to infinity for that. But you know how to take the limit. We have already done that once. So we will not bother to show you that again. These are not the only methods by which you can directly calculate the propagator for the free particle in the path integral formalism. But we will talk in the next video about methods for calculating, say, the propagator for the harmonic oscillator, which will be slightly more non-trivial compared to this. We will actually use a Gaussian integral method for that. We will also show you another method which can be used there. Of course, direct calculation of propagators is not really the be-all and end-all here. The real advantage of the path integral formalism will be clearer once we start applying them for other purposes as well. So that's all for later videos. Bye for now.